So notice that this intersection of gamma with R must be maximal as well, because if not, then I could make this ideal bigger, because notice that right. Or if n is not maximal, then note that nx is also proper, right? It must contain gamma, right? Because gamma, then we can write gamma is gamma 0 plus x f of x. And notice that this is in gamma, and this is in gamma, as x is in gamma. So since x is in gamma, then this is in gamma, and so the constant term's in gamma as well. So if because now you've got a larger set of constant terms. So what we have is n is maximal. We have m comma x is contained in gamma. And m comma x is maximal. And we've seen this earlier because r power x modulo the ideal m comma x is isomorphic to r mod m. And since m is maximal, this is a field. So, gamma. Basically, this whole thing hinges right here on this result right here, that x is in gamma, and this depends on that power series result, that if you start with a unit, you must be a unit. Okay. This next theorem here, proposition. I'm going to actually skip 5, 6, 8, and I'll let you look at it, because you can actually glean 5, 6, 8 from this theorem 5, 6, 9. So let's let R and S be commutative with identity. Mod S, a ring homomorphism. And oftentimes, as I said, we demand that ring homomorphism fix the identity of R, the identity of S, and I am going to enforce that here. If S1, S2, up to Sn is in S, then there is a unique we'll call it phi bar. Into S such that right. There's a unique such that phi bar restricted to R. So in other words, when I look at what I do to the constant terms of a polynomial, I get my original homomorphism up here. And phi bar evaluated that side. And this property determines of the isomorphism. So here's the deal. If I walk up to you on the street and I give you a homomorphism feed from R to S. So basically, this homomorphism tells you where to send all your coefficients of your polynomials. And this property right here tells you where to send each variable. So now I know completely how the homomorphism works. If I give you a f of x1 xn, then basically what you're doing here is you're plugging in S1 up to Sn for this, and you're using phi to adjust the coefficients. This property uniquely determines the polynomial ring and then variables up to isomorphism. And I'll leave that as an exercise, but it's fairly easy to see, because to determine the homomorphism, you have to know where one goes. You have to know where the elements bar go. That's taking care of phi. And then basically you have to know where each xi goes, right? And once you know where each I goes, the fact that it's a homomorphism tells you that you determined everything you need. Composition. And I'm going to use let's let R be an integral domain, and that's an R multiple set. A I'm using equals, fast, and loose because these are equivalence classes starting with different sets, but it's pretty easy to identify this. So what this is saying is, if I have polynomials with fractions out of the subset of R, this is the same thing as the fractions, the polynomial over the fractions. The power series, not quite so nice. There's actually an injection here. And let me outline why this is true, and I'll give you an interesting example. The claim here. So let's think about what this means might help to write it down. That's what that notation means. It means fractions with your numerator coming out of polynomials and your denominator coming out of the subset of R, right? Because remember, if S is a multiplicatively close subset of R, it's certainly a multiplicatively close subset of a larger ring RS. What I mean by this is these are actually polynomials that look like A0 or F0. Xn or A. Now, why are these the same? Well, it's pretty clear, isn't it? That anything that can be written in this form can be written in this form, right? Because you've got the single denominator S that works for everything. Why does the other way work? Well, because you can collect the denominators. Whatever the places it says, A0, S1, sin, A1, S0, S2, Sn, X, plus A, N, S0, Sn minus 1, Sn. So now, this is in. Where's my fractions at? Now notice, for power series, it's a little bit different. Because what is true is if I have A0 plus A1 X, AN XN, over S, I could certainly write this as A0 over S, A1 over S, X, AN over S, XN. So I get this claim containment here that a power series in the numerator and a single S in the denominator is contained here. But perhaps you see the problem. What I tried to do over here, right, when I put this inside the other one, is I collected the denominators. I've got problems doing that if I've got infinitely many denominators to collect, right? So for example, I'll give you an example. Let me give you the power series that you actually cannot do this for. If S is, in fact, for most S's, let S be the non-zero elements. If you have ZX localized to non-zero elements, notice if S is Z minus 0, this is Q power X, right? This is actually much, much bigger. Let me give you an example of something that is here that is not here. Consider the power series. again. All right. This is actually Q power x, but not in Q power x. Well, because the problem is I used infinitely many primes and I can't collect the denominator. Now, admittedly, this example looks like, oh, okay, that's a little bit fast and loose and hand wavy. All you've really kind of done is sort of convinced me that maybe doing this trick won't work. Maybe there's another way to do it, but actually, let me make a note here. This is from a paper from about the early 70s, I think. Large domain. And we'll say 0 is not an S. Then you get equality here. If and only if for every countable collection, this one. Yes. The intersection of the ideals generated by this is non-zero. Basically, what this condition says, let me make clear what I mean by this. That was a localization. What this means is you can find a common divisor of all these RSIs, right? For every countable collection, you can find a non-zero element that divides them all. Basically, that's what you need to be able to collect it over a single denominator. Intuitively, that's what that means, and it's not too difficult to show, actually. So let me demonstrate how rare this is. For example, even take something like the integers, which is a well-behaved thing. Suppose your multiplicative set has 2 in it. Well, it's a multiplicative set, so it's got 2, it's got all the multiples of 2, right? So it's got, or I should say powers of 2. It's got 2, 4, 8, 16, all those guys, because it's a multiplicative set. And notice, if you intersect the ideal generated by 2, 4, 8, 16, 32, etc., the intersection of all those ideals is 0. And so this actually is a pretty rare situation for that to work out. Okay, any questions? Okay. So now, as promised, I'm going to say a couple of things about factorization in polynomials and power series. Let me start off with something that we already know. So I'll skip the proof of this because we've basically done it. Proposition. If F is a field, then Fx and the power x are Euclidean. And recall the Euclidean function on the polynomial ring is the degree. And Euclidean function on the power series degree, or on the power series ring, is the order, the sort of the smallest degree. So here's what we know so far. Polynomials That's good. Euclidean domain, so in particular PID, so in particular the unique factorization of both of these. Now, here is a theorem that we will prove with the help of some of the stuff we talked about UFDs. R is a UFD if and only that is to say, whenever you have a ring that has unique factorization, its polynomial ring also has unique factorization. This is an incredibly important result. And it means some interesting things. In fact, one of the things it means, we will see later that actually what happens is a polynomial ring in any number of variables over UFD is a UFD. So any ring is the homomorphic image of a UFD. Proof. The fact that unique factorization in the polynomial ring forces unique factorization in the coefficient ring is not too difficult. See if you can show that. The interesting part, of course, is the fact that unique factorization in the coefficient ring is good enough to give it for all polynomials. So let's try that, shall we? So suppose R is a UFD. We show Rx is a UFD by showing any prime ideal non-zero of Rx contains a non-zero prime. Remember, that was our earlier characterization of UFDs. To UFD if and only if every non-zero prime ideal contains a non-zero prime element. So that's going to be basically our strategy. Okay, so let's just hit it. Suppose gamma in Rx is a prime. So suppose I have a non-zero prime. So consider take this prime ideal Rx and intersect down to R. In fact, whenever you intersect a prime ideal from a larger ring down to a smaller one, it's always still prime. That's easy to show. But if you're not comfortable, I can do that for you if you like. Everybody okay with that? When you intersect a prime down from the bigger ring, yeah, well, I'll show it. Here, A and B are in R. Suppose the product of these two are in P. Then, without loss of generality, A is in gamma, because this is a product of things that are in P, which is contained in gamma, because it's the intersection of this prime from a larger ring. Therefore, A is in gamma, and it's in R, which is P. So, let's take this non-zero prime ideal, intersect it down to R, and call it P. Case 1. P is not 0. In this case, with a UFD, all right, there exists I claim so. Suppose you have a non-zero prime ideal. We know that R is a UFD, so it must contain a non-zero prime element, or P is prime. Prime in R. I now claim that not only is this non-zero prime element in P prime in R, it's also prime in Rx. Right? So how am I going to show this? Well, consider PRX, which is it suffices to show that this element generates a prime ideal in Rx. This is what it looks like. Well, Rx mod Px by results we've done, so isomorphic to R mod P. And this is a domain. So this is the domain. So since it generated an ideal that was prime, it itself is prime. And so, conclusion, so what I've shown is, in this case, when I intersected gamma down and got a non-zero ideal, then I found a prime element in it that was still prime in Rx. Okay, good for me because I'm half done. Case 2. In this case, you've got to worry about what happens if the intersection down with the smaller range is equal, right? Because the theorem by UFDs talks about non-zero prime. So we got to get this space covered. Let me give you, can anybody think of an example of a gamma that has this effect? Can you think of a prime ideal in the polynomial ring whose intersection down with the coefficient ring is always a zero ideal? The ideal generated by X is a good example, right? Because the ideal generated by X will not have any constant terms in it at all, right? And so its intersection downstairs is zero, right? So certainly this case is a possibility of occurring. So how are we going to deal with this? Well, consider the multiple enclosed subset consisting of all non-zero elements of R. Right? Now, intersect R is zero. This implies that And so what do I get? Well, here's what you get. So gamma S this is our localization correspondence. You remember that business we had between, there's a one-to-one primes of Rx in this case, missing S and primes this is our localization correspondence. Under our assumption here, gamma intersect R is 0. That means that there's no overlap between gamma and the set of non-zero elements of R, which means that this survives. That is, it's a prime ideal still in this range. And bonus, this ring is where F is quotient of R. So this prime ideal of Rx misses S, so it survives as the prime ideal of Rx localized at S, which is Rs localized at X, but this is all the non-zero elements of R, so this is Fx. So gamma S is a prime ideal in Fx, which is a PID, because as we just pointed out, it is it's Euclidean, hence PID. So gamma S is generated by some Fx. And I can actually assume a couple of things. Assume a couple of things to make my life easier. Gamma S is generated by f of x, which ostensibly is a polynomial with coefficients in f. All right. So it's a bunch of fractions, right? It's a polynomial with a bunch of fractions. Number one, I can assume that f of x is in fact in Rx by clearing the denominator. And I can go farther, and if f of x is a0 plus a1x, a(n)xn with ai and r, I can assume the GCD of the coefficients is 1. Because if they've got a common divisor, I'll just divide it out. Because again, this ideal is in a field and every non-zero element is a unit. So I can divide out the constant. So this generator of this principal ideal here, I can assume is a polynomial in fx, but I can go further to make my life easier. I can assume that all the coefficients in fact are in R, and the greatest common divisor of all the coefficients put together is 1. Everybody with me so far? So notice that and so the ideal generated by f of x, and in fact, I'll go farther. In fact, f of x is in gamma, right? Because it was the generator of this gamma localized at s. So when I clear out these denominators, now it's actually in r of x intersected from this. So it's actually in gamma. So the ideal generated by f of x, let me make clear what I mean by this. When I say the ideal generated by f of x here, as opposed to here, here I mean it over fx, here I mean it over rx. The ideal generated by here is contained in gamma. So let me kind of outline where we're at here. What we've shown is this f of x is the generator of this ideal pushed up to k to fx. This special element generates an ideal inside of gamma. If I can show an equality here, then f of x prime and if I can show that this actually this f of x actually generates all of gamma, then I'm finished, because now what we have is my non-zero prime contains a prime element. In fact, it's generated by that prime element. And so that's the only thing remaining to do. Let's say g of x times h of x being in actually, I'm going to show something. I'll show something more general. If I can show f of x is prime, then f of x is a prime element. So to this end, I want to show this is a prime ideal. So g of x times h of x equals f of x r of x, where here g, h, and r are in rx. Now, what I want to do, of course, is I want to show that one of g of x or h of x is in this ideal. Equivalently, I need to show that f of x has to divide one of these two. Now, the first thing is, note, has an element of f of x divides g of x without loss of generality. Because if I were doing this, if I'm doing this computation in fx, we know that this thing generates a prime ideal, so it has to divide one of these two, and also it divides g of x without loss of generality. So g of x equals f of x k of x with k of x. Now notice here's the problem. F of x divides g of x, but its quotient actually is an fx. I'd really like to prove that's in Rx, because if I prove that's in Rx, then I'm done. Because now f of x is divided that in Rx. But notice the k of x can be written in the form m of x over a with m of x and r of x and a and r not 0. Again, this is due to this fact here. M of x is in here, so it can be written as a single denominator. So this k of x here, this is maybe not an element of Rx because it's got fractions here. So I'll write this over a single fraction this way, and I get this equation here. And again, I will assume that, oh, that's fine. So I get a g of x equals now write a is equal to p1, p2, pt with each pi and r prime. And so what I have is P1, P2, P, G of X, F of X, and X. Everybody okay with it? Now, notice that P1 divides F of X, M of X. And P1 is prime. And we've already proved that if it's prime in R, it's prime in Rx. So P1 has to divide but it can't divide F of X. Can somebody tell me why? What do we assume about F of X that keeps it from being divisible by any constant? The greatest common divisor of the coefficients of F is 1. And so there is no common factor of P dividing all the coefficients. This is an impossibility. Therefore, P1 divides M of X, and we'll say that M of X over P1 is M1 of X. So now we have P2, PT, G of X equals F of X and 1 of X, where these are both in R. Continue the process, and you get G of X, F of X, MT of X with MT of X. And that does it for you. So F of X divides G of X as an element of Rx. So F of X. And that concludes the proof, because we've now shown that any prime ideal of a polynomial ring, non-zero, contains a non-zero prime number. Okay, any questions on that? All right. Well, if there aren't any questions, you all have a good one, and we will see you on Wednesday.